Hi everyone, in this lecture we are going to discuss one example problems related to composite frames or composite structures in here. And in these problems we need to find the reaction forces at joint A and C, where joint A is a fixed support and joint C is a roller support. And we also have to find what is the pin connection forces at joint B. Okay. So this structure is similar to the one that we discussed in the previous lectures when we discussed the concepts related to frames and machines. Okay. So in solving these problems, it's always a good start to sketch the free body diagrams, right? Joint A is a fixed support, so we have AX, AY, and MA. This reaction moment MA is actually occurred at the joint A, but I just draw it a little bit far away for clarity. And then at joint C, over here we have a roller support, so we only have one reaction force is Cy. Okay, so if we observe this entire composite structures, there are 4 reaction forces, right? 4 unknowns, but we only have one free body diagrams, and those free body diagram consists of systems of coplanar forces such that we can write 3 equations, right? So if we just use this entire free body diagrams, definitely we cannot solve for all of the unknowns in here. Okay, so we have to make a cut later, and the cut that we are going to make is going to be at B. Okay, remember when solving these problems, when we make the cut, we try to make the cut at the connectors. Okay, in this case it's the pin connections. Okay, and also one thing that you need to remember is once you make the cut, you expose the internal forces at the connectors, and since it's a pin, we only have a vertical and horizontal connection force. Okay, and in here we have to find, right, reaction forces and pin connection forces. Okay, so let's start the analysis. In the analysis, we have to first sketch the free body cut diagrams, right? Once I make a cut right here, I separate it into left hand free body diagrams and then the right hand free body diagram. Okay, so this is A, this is B, okay, and then this is C, this is B. Okay, so in here we have AX, AY, and MA. Okay, then we have the distributed force is symmetric, right, with the magnitudes is located at the midspan of AB is 200 Newton per meter. Okay, at joint B we have a pin, so we have here is BX and then BY. Okay, and then on the right hand free body diagrams we also have BX and BY. Okay, then we have the 800 Newton joint force at the midspan of BC, and then we have the reaction forces at C, CY. Only one reaction forces because at C is a roller support. Okay, so if we analyze these 2 free body diagrams, the left hand free body diagrams alone without the pin connection forces is a stable structures. The right hand free body diagram alone without the pin connection forces is unstable. Okay, so we have to start, okay, from the right hand free body diagram first. Okay, so we start from right hand free body diagram. Okay, and before that, let's count how many unknowns we have. Okay, we have 1, 2, 3, okay, 4, 5, okay, and 6, okay. I didn't count this bx and by anymore because I already counted right here, okay. So we have 6 unknowns, right? And right now we have 2 free body diagrams, right? We have 2 free body diagrams, and in each free body diagrams we can write 3 equations each, right? So total we have 6 equations that we can write, so we should be able to solve for all of these unknowns right here, okay. So let's get continue. So we start from the right hand free body diagrams, and we can take some of the moment at B, okay. When I take some of the moment at B, there's no contribution from Bx and By, and the only contribution is from Cy, right? And the distance right here is given in the problems is 4 meter, and this causes counterclockwise rotations or moments about point B, so it has a positive sign, okay. And then the 800 Newton force is located 2 meter away from point B, so we have 800 Newton times 2 meter, okay, and this force causes clockwise rotations, so it has a negative sign, and set it equal to 0, okay. Solving these expressions, I obtained that my Cy is equal to 400 Newton, right? And then doing sum of the forces in the y, I have Cy minus By minus 800 Newton equal to 0. Since I know Cy is 400 Newtons, I can calculate my By is equal to negative 400 Newtons. It means that the actual direction has to go upward instead of downward, as I assume in here, okay. However, let's keep it downward, and when we try to calculate later, we will use this negative value that we have obtained, okay. And if we calculate sum of the forces in the x equal to 0, we will and set it equal to 0, we will obtain that Bx is equal to 0, okay. So in here we have already solved for 3 forces, okay, 1 reaction forces and the pin connection force, okay. Then afterwards we continue with the left hand free body diagram. We already calculate that By in here is negative 400 and Bx is 0, okay. And we can further simplify this distributed load into a resultant force located at the midspan, okay. Let's call it R, okay. And that R is 1/2, which is the area of the triangle, right? 1/2 times the length of beam AB is 6 meter times the height is 200 Newton per meter. So in here I have 600 Newton, okay. So R is 600 Newtons. It's located 3 meter away from A, which is the centroid of the triangle, okay. And to solve for the unknowns, we can take some of the moment at A. Thus in here we will eliminate AX and AY, and we will be able to calculate what is MA, okay. So in here we have MA, which is the reaction moment at A due to the fixed support, okay. And then we have negative R times 3 meter, okay. And then we have By times 6 meter, okay. MA is counterclockwise, so it has positive sign. R is clockwise with respect to point A, so it's a negative sign. By is counterclockwise, so it has a positive sign, okay. And set this expression equal to 0, we will be able to obtain that in here MA is equals to r times 3 minus by times 6. Okay, then if my calculation is correct, you should obtain 4200 Newton meter. Okay, and remember, so when you plug in the by right here, you have to plug in negative 400 newtons because we stay consistent with the result that we have obtained in the right hand free body diagrams. Okay, so once you obtain your MA, we can do another we can write another equation, equilibrium equations, and let's write some of the forces in the x equal to 0. In here we have ax positive going to the right plus bx positive going to the right, and those are the only forces in the x directions, so my ax is equal to 0. Okay, the final equilibrium equations that we can write from the left hand free body diagram is sum of the forces in the y. Okay, so we have ay positive going upward, and then we have negative r negative going downward, and positive by because it's going upward, and set it equal to 0. So in here my ay is r minus by. R is 600 plus by is negative 400, so my ay is 200 Newton. Oh, this should be right here, it should be negative, right? Negative of negative, it becomes 1000 Newton. Okay, all right, and I think with that we already calculate all of the 6 unknowns that we encountered in these 2 free body diagrams over here, right? And if you would like to calculate the pin connection forces, right? So the pin connection forces, the resultant of the pin connection forces is the square root of bx squared plus by squared, right? And bx is 0, right? And by is negative 400 Newton square. So in here b is 400 Newton. Okay, and we have obtained that cy is 400 Newton, right? And then ax ay 0, ay is 1000 Newton, and ma is 4200 Newton meter. Okay, so there's one more thing that I would like to say, that since the composite structure can be divided into the stable portion and the unstable portions as it describes in here, you can see that all of the forces, right, that is applied to this unstable part will be distributed to the stable part. Okay, however, the forces that is applied on the stable part will not be distributed to the unstable part. Okay, I repeat again. So all of the applied forces, right, that is applied in the unstable part will be distributed to the stable part as shown in here through the pin connection forces bx and by. However, the applied forces on the span AB, which is the stable part, will not be transferred to the unstable part of the composite structures. Okay, with that in mind, I think it's not enough for these lectures. Please let me know if you have any questions, and thank you for listening.